In the previous video, we introduced the gas laws. These are four simple little relationships that describe how the pressure, temperature, volume, and number of moles of a gas all affect each other. They were all based on fairly simple observations. All else being equal, you expect a balloon to expand when you add more gas into it, or when you heat up the gas inside, for example. The unanswered question we had from last time is, well, what can we actually do with these relationships? In this video, we're going to see how we can leverage the gas laws to actually solve problems. And in a bit, we're also going to see how we can combine all the gas laws together into one master equation that covers everything at once, the ideal gas law. For starters, though, let's consider one of the individual gas laws. We mentioned last time that these are proportionalities and not equations. Just in case it's been a while, this sign does not mean that the pressure of a gas is always equal to its temperature. Rather, it means that if one of these properties changes and everything else stays the same, the other property changes in the same way. And that's really the key here. The individual gas laws aren't much use if you want to know something about a single set of conditions, but if you want to predict changes, they can come in really handy. It works like this. Amundsen's gas law states that a change in temperature will reflect a predictable corresponding change in pressure as long as everything else about the gas stays constant. These properties are linked. They change according to a fixed ratio. So we can actually rewrite Amundsen's law like this, where the ratio between the pressure and temperature is equal to a constant. We're not going to define what that constant is, and it actually doesn't matter. The important thing is that this equation tells us that the value of this ratio on the left will always be the same. So here's how you could use Amundsen's law to solve a problem. Say you're starting with one set of conditions, maybe a gas at 2.5 atmospheres of pressure, and its temperature is something like 150 Kelvin. Now say you want to heat the gas up to 400 Kelvin, more than double what we had before, and you want to know what's going to happen to the pressure. Well, Amundsen's law says that as long as you didn't change anything else, like the volume or the amount of gas present, the ratio of the pressure and the temperature will always be the same. So we can actually take these two different conditions, one of which has an unknown that we want to figure out, and set them equal to each other. Now we have one equation and one unknown, and we can solve using algebra for P2 to get the final pressure of the gas. You can do this with all the gas laws. And when you rewrite them like this, you end up with a bunch of useful tools for predicting the effect that a change in one property will have on another property. We're not going to run examples using all these rewritten laws during this video. You'll see plenty of practice in our other course materials. But there are a couple of quick things that you want to watch out for. Point number 1. Boyle's law looks different. Most of the gas laws, if you'll remember, are direct proportionalities, meaning that they describe a situation where changing one property causes the second property to change in the same direction. You'll recall, though, that Boyle's law was different. It describes how pressure and volume are inversely proportional. So as volume goes down, pressure goes up. They're changing in different directions. The algebra you'd use to get you the equation is still the same, but because it's an inverse relationship, we end up with a form that looks like this. P1 times V1 equals P2 times V2. Just something to remember. It looks different than the other gas law relationships. Okay, point number 2. Always use Kelvin for your temperatures. Units usually don't matter when you're doing these kinds of ratio calculations as long as you stay consistent with your units. But a big exception to this is with temperature values. Using Fahrenheit or Celsius will sometimes work with these equations, but the only scale that will never let you down is Kelvin. Remember, and I know this was a long time ago, Kelvin is the temperature scale that never goes negative. 0 Kelvin is absolute zero, which is a theoretical cold limit that we can't actually get to in real life. So, using the Kelvin scale helps you avoid some awkward problems with the other temperature scales. You never have to worry about your calculation erroring out because you divided by 0, or giving you a weird result because you plugged in a negative value for temperature. Just use Kelvin all the time, and you'll be safe. And with that, we can move on to the main event. The individual gas laws are great for looking at changing conditions, but they're like little fragments of a bigger picture. None of them completely describe how the properties of a gas are linked together, even though you might have noticed that there is quite a lot of overlap between them. Well, it turns out that scientists in the 1800s noticed this too, and they went ahead and put everything together for us, putting the individual pieces together into a master equation that relates all four properties together at the same time. This is called the ideal gas law, and it's one of the most important equations you'll be using in the first half of this unit. For once, we have an equal sign right out of the box, which means that we can do algebra with this equation to solve for some unknown property of a gas, as long as we know something about the other properties. You'll get questions like this a lot. You'll be told that a gas has a certain pressure, volume, and temperature, for instance, and then you'll be asked for the number of moles of the gas. Hopefully, we can see how this would play out. You just solve for the missing quantity. Oh, and of course there's one more thing here, that new letter R in the equation. R is called the ideal gas constant, and it's basically just a conversion factor that helps all the units work out in the ideal gas law. However, this is a good time to warn us about being careful with units again. We'll encounter a couple of different versions of R during this unit, but the most common one with this equation has a value of 0.08206 liters times atmospheres over moles times Kelvin. You'll often have access to this number in the reference materials for a problem, but in order to use it, you better be sure that the pressure, volume, moles, and/or temperature that you're plugging in are all in the proper units that will cancel appropriately with this version of R. There are a couple of more tricks we can do with the ideal gas law, and they all have to do with rearranging the equation. For starters, it turns out that if you do a little shuffling and make one substitution into the original formula, you can actually get an expression that gives the molar mass of the gas in terms of its density, pressure, and temperature. You might want to use this version to help speed things along when certain calculations in your homework. And although we won't go into an exhaustive derivation right now, it's important to recognize that we haven't done anything fancy here. It's just a rearrangement and relabeling of a couple of variables. The second trick is similar, but it's one of my favorites in this unit for just simplifying your life a little bit. Say you have to do a bunch of gas law problems, but you don't want to remember all the individual gas laws. Well, it turns out you can use the ideal gas law alone to help you remember all the other ones. Let's take a problem like the one we did earlier. Say we're told that a certain gas is at 3.5 atmospheres of pressure in a 5-liter container. Now we compress this gas down to 3 liters and we keep everything else the same. And the question is, what's the new pressure? If you remember Boyle's law, you can just write that out and solve for the unknown. But let's pretend for a minute that we only know the ideal gas law. In this problem, we have two different conditions: before the gas was compressed and after. But we're told that the amount of gas and the temperature don't change. So actually everything on the right side of the ideal gas law will be the same, before and after. This means that we can just set the two left-hand sides of these equations equal to each other. And there you go. You just constructed Boyle's law from scratch. Let's take another example. Maybe you have 4 moles of a gas taking up 2.5 liters of space. Let's say that some kind of chemical decomposition reaction causes the gas molecules to break down. So now we have 8 total moles of gas at the end of the reaction. And the question is, what's our new volume if the pressure and the temperature stay constant? Well, we have the same situation again. 2 different conditions where 2 variables are changing and 2 are constant. This time let's do a little reshuffling so that the changing stuff is all on one side of the equation and the constant stuff is on the other side. As soon as we've done that, we're basically finished. You can set the 2 left-hand sides equal to each other, just like we did before, and you've successfully written Avogadro's law without having to remember anything new. Then we just plug in and solve for the missing volume. One more example before we finish up. Say we have a gas that starts at 273 Kelvin in a 3-liter balloon under 1.5 atmospheres of pressure. This time, we raise the temperature up to 313 Kelvin, and we also increase the outside pressure to 5 atmospheres, and we want to know the new volume. We can do the same thing again here. Let's write the ideal gas law, and move it around so that all the changing stuff is on one side, and all the constant stuff is on the other side. Then we can set the left-hand sides equal again and solve. Pretty simple approach, really, and it works for every kind of problem like this that you could imagine. Incidentally, the relationship that we ended up with this time is sometimes called the combined gas law, because it's basically a combination of a few of the individual gas laws together. Anyway, that's all we have this time, and it should be enough to get you going on some of the core problems that will make up most of the first half of this unit.